All right, everyone. So welcome to the seventh week of the AMC10 Basic class. And so it's going to be about counting today. And so while we wait for more people to come in, please work on the fun problem of the day. Oh, and also for people who don't know what expected value means, it basically means the probability of each outcome times the value of the outcome. So for example, the expected value of the roll of a fair cubical die is just 1/6 times 1 plus 1/6 times 2 plus all the way to plus 1/6 times 6. And this is for cubical die. Of course, it's not the same for an octahedral die. All right, so I'm going to start going over this problem now. So this problem is okay. So this problem is very similar to the example of a cube that I gave earlier. And so the expected value of the roll of a fair octahedral die is 1/8 times 1 plus 1/8 times 2 plus all the way to plus 1/8 times 8. And then if we add up 1, 2, 3, and so on, you just get that this is equal to 1/8 times 36. And as a decimal, this is 4.5. So are there any questions about this problem? All right, if not, I'll move on. So this is week 7, and we're going to go over counting and probability. So this week we're going to cover stars and bars, the Pascal's triangle, the binomial theorem, probability, and expected value. So stars and bars. So stars and bars are used to solve problems of the form. How many ways can one distribute k indistinguishable objects into n distinguishable bins? And so you can imagine this as finding the number of ways to drop K balls in N urns, which is why it's also called balls and urns sometimes. And this is also equivalent to arranging K balls in N-1 dividers. And in this case, the K balls are represented by a star, and each divider is represented by a vertical line. Okay. And then, so for example, this, and this, these represent some of the ways to put K equals 4 objects into N equals 3 bins. And so the number of ways in which you can do so is always N plus K minus 1 choose K. And because N choose K is also N choose N minus K, you can rewrite this as also N plus K minus 1 choose N minus 1. And so here's your first exercise. What do you mean by the 23rd, not the 22nd? Yeah, I know the date is slightly wrong, but that's just because Overleaf doesn't use Pacific time as its standard date time. All right, so I'll start going over the problem now. So you can casework off of how many. Okay, so first of all, Prentice has $5 and 10 pence, and the 10 pence are identical. And so, how many ways can he hand them out to his daughters if two of his daughters must get the same number of pens? And but you don't need every daughter to get a pen. All right, so now you can casework off of stars and bars can't really apply to the whole problem in general because you have an additional restriction here. And so you can casework off of the number of pens that Charlotte and Emily get, and then from there you can use stars and bars. So case one, both of them get 0 pens. And then so you're calculating the number of ways such that 3 numbers add to 10. And so by stars and bars, you can easily see that this is just 12 choose 2, which is 66. And now the second case, each of them get 1 pen. And then in this case, it's 3 numbers that add up to 8. And then by stars and bars, this is 10 choose 2. Similarly, the third case is 2 pens and is 8 choose 2. Fourth is 3 pens and 6 choose 2. The fifth is 4 pens each and 4 choose 2. And the final case is each of them get 5 pens and it's 2 choose 2. And these are equal to 66, 45, 28, 15, 6, and 1. And so you can add these numbers up. And the result you should get is 161. So are there any questions? All right. If there are no questions, then let's move on to the second exercise. All right, so I'll start going over this problem. So you're selecting 6 cookies, and the tray has chocolate chip, oatmeal, and peanut butter cookies. And so you're given that there's at least 6. And so that means you can choose the 6 cookies from the chocolate chip, oatmeal, and peanut butter cookies with no restraints. And so you want to find how many different ways you can choose 6 cookies. So this is a pretty standard stars and bars problem. So you have 6 cookies, and so that makes 6 stars. I'll just draw the stars as circles because it's faster. And you're dividing it into 3 groups, so you need 2 dividers. And so the number of ways to arrange this is just 6 plus 2 choose 2, which is 8 choose 2. And if you expand this out, it's equal to 28. So are there any questions about this problem? Pascal's triangle. So in Pascal's triangle, if none of you have ever heard what it is, it's basically a triangle where the sum of each number is the sum of the 2 numbers above it. So 1, 1 goes to 2, and the numbers on the very sides are 1. 1, 1 and 2 goes to 3, 2 and 1 goes to 3, 1, and you can continue the pattern here. And so there's many patterns you can find in Pascal's triangle. So one of them is that this row adds to 1, this row to 2, this row to 4, this row to 8, and each time you increase by 1 power of 2. And this holds true for all rows in Pascal's triangle. And this is just a brief mention of the hockey stick identity. And so it's basically saying that any row in the sum of numbers here is equal to the number here for any number in any row in Pascal's triangle. So like here, 1, 2, 3, 4, 5 adds up to 15. And here, 1, 4, 10, and 20 add to 35, and so on. And mathematically written out, it's this. And so now we're going to go over what the binomial theorem is. So the binomial theorem is basically a formula for the expansion of the sum or difference of 2 terms. And so for real or complex, you don't need to understand what complex means right now, but it basically means a number with an imaginary part. So for any numbers a and b and a non-negative integer n, you have that a plus b to the n is equal to this, where n choose k is this, as usual. And so, and when like terms are collected, are the same as the entries on the nth row of Pascal's triangle. And this is not a coincidence. And so this is an example of what a binomial is. And so here's a way to see the binomial theorem in action. So when you square a plus b, the coefficients are 1, 2, and 1. When you cube it, it's 1, 3, 3, 1. And when you raise it to another power, it's 1, 4, 6, 4, 1. And if you go back to the Pascal's triangle, you can see 1, 1, 1, 2, 1, 1, 3, 3, 1, and 1, 4, 6, 4, 1. And so this is Newton's identity. And so if you think of the numbers on Pascal's triangle as binomial coefficients, or n choose k, which they are, then you can see that this holds true. And the same thing holds for this. And so here's an example for the binomial theorem. All right, so I'll start going over this problem. So in Pascal's triangle, so this just tells you what Pascal's triangle is. And so you want to find the row of Pascal's triangle in which 3 consecutive entries occur, and they're in the ratio 3, 4, 5. And so 3 consecutive ratios can be expressed in the form n choose r, n choose r plus 1, and n choose r plus 2. And so from the 3 to 4 to 5 part, we have that n choose r divided by n choose r plus 1, which can simplify down to r plus 1 divided by n minus r is simply equal to 3/4. And you have that n choose r plus 1 divided by n choose r plus 2, which you can simplify down to r plus 2 divided by n minus r minus 1 should equal to 4/5. And so from here, you can expand both sides. So 4r plus 4 equals 3n minus 3r. And 5r plus 10 equals 4n minus 4r minus 4. And so 3n equals 7r plus 4, and 4n equals 9r plus 14. And when you solve these equations, you should get that n is just equal to 62. So are there any questions? All right. If not, let's move on to the next problem. Alright, I'm just gonna give a short hint. Take a look at the terms that are not zero. And do you recognize these terms? Alright, so I'll start going over this problem now. So you want to factorize 10070350350 I probably messed up pronouncing that somewhere along the line, but whatever. So you should be able to see that the terms that I've circled are the 7th row of Pascal's triangle. And so if you notice, these terms are 1 plus 7 times 10 cubed plus 7 choose 2 times 10 to the 6th, where this is the 1, this is 7, this is at 21, plus 7 choose 3 times 10 to the 9, plus 7 choose 4 times 10 to the 12, plus 7 choose 5 times 10 to the 15, plus 7 choose 6 times 10 to the 18, plus 7 choose 7 times 10 to the 21. And so by the binomial theorem, we can now see that this is 10 cubed plus 1 to the 7th. And so this is 1001 to the 7th. And so you should know that 1001 can prime factorize as 7 times 11 times 13, or at least remember one of the factors and be able to find the others. And so this is prime factorized as 7 to the 7th times 11 to the 7th times 13 to the 7th. So are there any questions? All right. If not, I'll be moving on. So, probability. So, probability represents the likelihood of an event happening. It's not the actual chance that it will happen. So, the probability of an event happening is defined to be in the range from 0 to 1, where an event with probability 0 will never happen, and an event with probability 1 will always happen. So if all outcomes are equally likely, the probability of event E occurring, which is defined as P of E, is just the number of successful outcomes divided by the total number of outcomes. So we're a bit short on time, so I'm just going to skip this problem and move on to this one. All right, so I'll be just going over this problem now. So you have a pair of standard six-sided fair die. And so the sum of the numbers determines the diameter of a circle. And note that it says diameter here. And so you want to find the probability that the area is less than the circumference. So first of all, we can find under what conditions is the area smaller than the circumference. So the area of a circle is pi r squared, and this has to be less than the circumference, which is 2 pi r. And so you can divide out pi r, and you're left with r is less than 2. And so this means that the diameter, which is 2r, is less than 4. So the diameter can be 2 or 3, because the smallest possible value of a pair of fair die, the smallest possible sum is just 2. And so the chance that the die roll is 2 is 1 times 1 over 36. And the probability that the die roll is 3 is 2 times 1 over 36. And so you can add these up because they're obviously exclusive. So this is 3 over 36, which is equal to 1/12. So are there any questions? If not, I'll move on to the next question. So in here, you should use geometric probability. And geometric probability is similar to normal probability, except you graph the thing you want to find on a plane, on the coordinate plane. and then it's the area that you want to find to happen divided by the total area. All right. So I'll start going over this problem now. So Billy and Cindy want to meet at their favorite restaurant, and they decide to do so at sometime between 1 and 2. And so they don't decide on an exact time, so they'll arrive at a uniformly random time between 1 and 2. And so Billy is impatient, and so if he has to wait for Cindy, he'll leave after 15 minutes. And Cindy will always wait for Billy until 2 once she arrives there. And so you want to find the probability that Billy and Cindy will meet. So to do this problem, we can first graph it on a coordinate axis. So let the x-axis be Billy's arrival time, and let the y-axis be Cindy's arrival time. And so these both go from 1 to 2. Okay, 2. So 130, 145, and 150. And 1, 115, 130, 2, 145. And so you can consider the square. You can consider the square as the total chance of Billy and Cindy possibly meeting. And so because Cindy will always wait, it's better to calculate the chances that Billy and Cindy will not meet. And the only way this is possible is if Billy arrives more than 15 minutes before Cindy arrives. So the probability of this happening is the line from 1 and 115, 115 and 130, and everything else above it, all the way to 145 and 2. So the probability that they will not meet is the shaded area. And so this has, if you let this have a length of 1, then this, okay. If you let the whole square have a side length of 1, then this length is of 3/4. And so the area of the shaded area is 3/4 times 3/4 divided by 2. And the total area of the square is now 1. And so the answer is just the shaded area divided by the total area of the square, which is 9/16 divided by 2, or 9 divided by 32. So are there any questions about this problem? Yes. And then this is the probability that they won't die together. And the probability that they will die together is 1 minus this, which is 23/32. Sorry about that. All right. So I'll move on to expected value now. So as I said at the beginning of class, expected value at its simplest is basically just the sum of the probability of an event happening multiplied by the value assigned to the event. And so there's a theorem called linearity of expectation. And so the expected value of a sum of random variables is always equal to the sum of the expected values of each variable. And it doesn't matter if the events are dependent or codependent or independent. And so another useful tool in probability in general is states. So they represent information about the behavior of a certain probability. And so the two is heads or tails, like here. And one way you can think of this, another way you can think of this is if a problem asks about something moving on a cube. And then you could set the states to which one of the 8 vertices it is at currently. So there will be a total of 8 possible states on this cube moving scenario. And one of the states is a very useful tool by itself, and it's probably one of the most useful tools in expected value beside the linearity of expected value. And so another thing in probability is recursion. So it expresses the probability of something occurring in the states, which is dependent on the probability of other states and most likely earlier states. And you can also see this in algebra or something like that. So for example, the well-known Fibonacci sequence is defined as the sum of the previous 2 terms. And that's another kind of recursion. And so this is a problem, but since we're out of time, I'll just directly start explaining how you do this. So Amelia has a coin and it lands on heads with probability 1/3. And similarly, Blaine has a coin that lands on heads with a chance of 2/5. And so they alternately toss their coins until someone gets ahead. And the winner is the first one to get ahead. Amelia goes first. And so you want to find the chance that Amelia wins. So let's, for example, P be the probability that Amelia wins. So P is simply the chance that she wins on her first turn. Plus the chance that she gets another turn back. And so times P, of course. And so the chance that she wins first is clearly 1/3. And the chance she gets another turn is the chance that Blaine's coin lands on tails, which is just 3/5. And also, another requirement of this is that her coin did not land on heads. And this has a probability of 2/3. And so you have that P is equal to 1/3 plus 2/3 times 3/5 times P. And so this tells you that 3/5 of P equals 1/3, or P equals 5/9. And so Q minus P is just 4. So are there any questions? All right. If not, that's it for today's class. Thank you for coming. And the handouts and homework will be posted in the Google Classroom soon.
Wait, I have
And,
a question.
okay.
Like when you do 2/3 times 3/5 times p, why do you multiply the p?
So this is a chance that she gets her turn back times the chance that she wins on that turn. And so P is the chance that she wins. Yeah.
Okay, thank you.
All right. And next week there's going to be a special event. And so that's it for today's class. Bye.